Here we're studying constant acceleration. We found equations that are valid anytime we have a constant acceleration, so that could be for some sort of mechanical means. If we have a car or a piece of machinery that we can control the acceleration, we can force that acceleration to be constant. But we'll also find that there are various special cases of constant acceleration that exist naturally. One of these examples is what's called free fall. Free fall is when an object is moving under the influence only of gravity. And so what we'll see is that in vacuum, so when there's no air resistance, every object is in free fall and will have the same acceleration regardless of the mass. We see that here in this picture. This is a time-lapse photo, or a strobe camera photo of a apple and a feather that are being dropped. We have a device here that has a trap door that falls out from underneath these two so that they can fall at the same time. They're falling into vacuum here, and notice how they fall in the same distances in the same amount of time. If we make a motion diagram here, notice how the particles are getting farther apart, indicating that there is an acceleration, a downwards acceleration. That is the same for both of them, and that is this acceleration due to gravity. In real life, we're not in vacuum. In real life, we have air resistance and the like, but if we have heavy objects where the weight of the object is significantly more than free fall, so nothing like a styrofoam ball or something like that, and as long as we're not falling very far or not going very fast, so again, not falling thousands of feet or not going hundreds of miles per hour, as long as we're avoiding all of those, then free fall is a decent approximation. And when we're in free fall, we have this acceleration of 9.807 meters per second squared. This is called g. G is the free fall acceleration, and it's the free fall acceleration due to gravity. G is assumed to be a positive value. You don't want to have a negative quantity hidden inside of a variable like this. So since we know that gravity causes us to fall downwards, the acceleration in the y direction, because gravity acts vertically, it would be negative g, right? The g is the amount of the downwards acceleration, and then the negative sign means that we're falling downwards. It's also common to measure acceleration in units of g, so that 1 g would represent 1 meter per second squared, 2 g's would be 19.6 meters per second squared, and so forth. So if you have an object in free fall, we would have a constant downwards acceleration. We just said that the magnitude of this acceleration would be g, which I use 9.807 to give myself 4 significant figures, so that that's not going to be the limiting factor in my calculations. If you drop an object, that object is going to accelerate downwards due to that acceleration due to gravity. If acceleration is constant, then that means that velocity is going to be linear, because the acceleration is the slope of the velocity. If the acceleration is negative 9.8 because we're accelerating downwards, our velocity would have a downward slope that way. Notice also that if you throw an object upwards, the object slows down as it goes up, and then it speeds up as it comes back down. So as it's traveling upwards, it has a deceleration. It's slowing down because the acceleration is downwards. The magnitude of that acceleration is still the same. This acceleration g is due to Earth's gravity, and as long as we are in the vicinity of Earth's surface, our downwards acceleration caused by that gravity is approximately 9.807 meters per second squared. To drive this point home, we call this value g the free fall acceleration. This is the acceleration due to gravity, but it is not gravity. Gravity itself is a force caused by the Earth's mass attracting the mass of all the objects around it. We will see later that Earth's mass creates a force. The force of Earth's gravity causes objects to accelerate at a acceleration g, which is our free fall acceleration, or our acceleration due to gravity. We'll see later as well that the gravitational pull depends on the size and mass of a celestial body, like a planet, like a star, like a moon. So there would be a value of g on the moon, there'd be a value of g on Mars. That would be a little bit different because the moon and Mars both have different size and mass. The spin rate of the celestial body also comes into play. We'll see that later as well, that a faster spin rate makes a lower value of g. So depending on where you are, near the equator or near the poles, we'll see that g would be slightly different. It's a little bit more of a complicated quantity, but the value that we're using is kind of an average value that gives us a good estimate of g. If we needed a more precise value, we could get one to complete our calculations with more precision. But for most of what we're going to do in this class, we're going to assume that g is essentially constant everywhere on the Earth's surface. That's not fully correct, but it is a reasonable approximation. Related to g, which is our free fall acceleration, that's the acceleration going straight down, we also have an object that could be on an incline. An object on an incline is going to accelerate down the incline. You can imagine that the steepness of the incline, the angle, is going to affect how much the object is going to accelerate down that incline. If we drew a motion diagram, we would expect the object to accelerate at a constant rate because fundamentally the object is sliding downhill because gravity is pulling it downwards. So in practice, what this means is that gravity is pulling on the object and the free fall acceleration of the object should be acting straight down. But the object is constrained to move along the incline, so only this component of that overall acceleration would be realized. Again, assuming if we have a frictionless surface and whatnot. Again, we'll see these details, we'll see this in more detail later on. But what we can see here is that if the total gravitational acceleration is straight down, the block is only seeing this component of that acceleration, and this side here is opposite that angle of incline. Again, we'll see a little bit more geometry later to prove that to be true. And so this would be the opposite. The full value of the free fall acceleration is g. That is the hypotenuse. And if this is opposite, that means that we'll use the sine. And so we can use this acceleration for the magnitude of the acceleration parallel to an inclined surface, where g is our free fall acceleration, theta is our angle of incline, and we're assuming no friction, we're assuming no air resistance or anything else, but we can explore this relationship as well. So although constant acceleration seems like a fairly limited assumption to make, we see that there's actually many situations where we have constant acceleration.